So I'll start with this presentation today. I'll explain about my background in research, the research work I have done in past few years, and currently the research area I'm active with. So primarily my research work spans across three major areas. It's about the first part here is about CMOS and MEMS, their integration using the Foundry platform. I have worked with TSMC and UMC foundries in Taiwan under university research program and have made several tape outs during that time span. So the purpose of this research was to show the single chip integration of micromechanical components and the electronics on a single silicon die. So this is quite widely perceived area in nowadays. Second area is using the same micromechanical devices and show their usage for several physical, chemical, and biological applications. So in that aspect, I have worked with the coupled oscillatory sensors and showed their applications for a couple of applications that I'll highlight and explain as we move ahead. And the third area that I have worked upon and currently I'm also very interested to explore is to utilize low cost rapid micromachining techniques to design and develop several devices, micro components for variety of applications. So in that aspect I have used the direct laser micromachining as opposed to the conventional clean room semiconductor fabrication. We can also use 3D printing and all those aspects are there. So first part that I would like to present is here on the left top. See the optical micrograph and the ACMs of the fabricated micromechanical transducer. So what I did here is that I have designed a micromechanical resonator which right top shows the FEM modeling, which allows us to determine the mode shape of this transducer, determine the resonant frequencies of the transducer. So here we can see that depending on the geometry, material properties, I was able to determine the frequency, resonant frequency, and the mode shape. So here the fundamental mode and the higher harmonic mode of the one geometry, the bottom are the second geometry, and the fundamental and the higher order mode. So this device also features inherent differential transduction, so that helps us to improve device performance. Then as I mentioned before, I utilize the typical CMOS circuit fabrication process where we actually fabricate our design and fabricate our chips. So what I did is use the foundry layers such as polysilicon, metals and oxide to implement this device. So here is the parallel plate capacitive transducer, and there is an air gap here between top electrode and the bottom electrode. So I also use some innovation here using the same layer. The original capacitive gap is about 1 micron, but using the pooling technique I demonstrated sub-micron gap to enhance transducer performance, such as which can help in implementing the oscillators, filters and all those things. Here is the measured spectrum of the two devices. Top is the low frequency device and the bottom is the high frequency device. So here is the resonance approaching 0 dB, and the phase in red at the resonance phase shift is 0 degree. It was a perfect condition to implement the closed loop, which is a combination of circuit and the MEMS device in a single silicon die, and show the oscillator. So this paper won the first prize in the IEEE Sensor Conference that year. More than 1,000 abstracts were submitted that year, and this was the research work in that case. So as an extension of this paper was also published as an invited special issue in the IEEE Sensor Journals. Moving on to the second aspect of my research area, as I mentioned, is the coupled oscillatory sensors. So what people have been doing is that using a one mass spring damper physical transducer. Instead of that, we use two physical transducers and couple them with the spring here. So the geometry and the symmetry conditions are such that both masses are equal, their springs are identical or equal, and their dampers are also identical. The only difference is that they are coupled by a very weak spring. So what we can do is that we can use this differential equations of the coupled oscillatory system to model this system. Once we have these coupled oscillatory equations, we can actually model the forces acting on the individual masses in this coupled system. So it's basically a summation of all the forces that equals to mass times the velocity, the acceleration actually. So the basic principle of operation is that if we make this middle spring much weaker than individual spring of the resonator, and if we disturb any one of the spring or any one of the mass, in scientific terms we say that we perturb this perfectly symmetry system. We perturb it with some disturbance or perturbation, and because of that symmetry gets broken, and the effect is that oscillation pattern gets disturbed, and that becomes our viable output of this sensor. So we have two outputs of this oscillator, which is coupled oscillator. We can go for a traditional way of measuring the shifts in the resonant frequency, which is similar to what we do with the single oscillators. Instead of that, we now detect the mode localization effect, which is once the symmetry is broken because of the perturbation, the energy, vibration energy, gets localized to a small geometric region of this physical transducer. In simple terms, we say that one oscillator vibrates with a higher amplitude as compared to other oscillators. So we can sense the amplitude vibrations instead of sensing the frequency shift. So we sense the amplitude shift. So that's called as mode localized sensors. And this I have done quite a theoretical and analytical work on this topic. Here is the application of this topic. So what we do is that instead of one resonator or oscillator, we have three oscillators, and they are electrically coupled to each other, and we have driving and sensing arrangement, and we show the application of this coupled oscillator as a biosensor. So what we do is that we take it to the laboratory, and one of the surface of these device is used to deposit a biomass. So we use some silicon beads to deposit these nanoparticles on the surface of the resonator. Here is the process of depositing that. Here is the optical, here is the measurement results. So if here we see that on the y-axis we have different output metric like frequency shifts, amplitudes, and amplitude ratio. And as we go on increasing the deposited mass concentration, the all outputs show the changes. And here we saw that the amplitudes have higher possible shifts as compared to the resonant frequency shifts. So that's why we say that the amplitude ratio based sensitivity is much higher in this kind of sensor. So we recommend this sensor to be used. The major advantage of this particular sensing, which is very getting pursued all over the world from all over the researcher, is that this test has been done in the ambient condition. We don't use vacuum to put this mechanical device, and we don't need standard conditions. So it's a very good example to use this device towards field application. So the limit of detection was about 180 nanogram concentration of the mass deposited. So here is the numerical models that were published recently. I published this with the IEEE sensor journals, and for the first time I derived this equation and presented them in a systematic manner. Here, because there are two oscillators, so we have two mode shapes and two resonant frequency. One is called in phase, and here on the right top we have out of phase. So here the graph shows how these mode frequencies will vary as a function of applied perturbation in both the positive and negative magnitude of the perturbations. Here are the governing equations showing that out of phase and in phase frequencies vary, how they vary as a function of perturbation. Here the graph shows instead of frequencies, what about we focus on the amplitude. Here it shows how the amplitudes vary as a function of applied perturbation. So here we see that if we make the middle spring coupling the two oscillators much lower, than the individual spring, we have the higher shifts in the amplitude, and that becomes our sensor output. So here are the governing equation for the frequency shift output. Sensitivity theoretically is limited to 0.5 maximum. However, if we have the relative sensitivity, amplitude ratio based sensitivity is given by this equation, which is spring constant divided by the twice the coupling spring. So the conclusion for that, the amplitude based sensitivity was K effective times Kc, K effective by Kc times more sensitive than the frequency shift output. And coming back to the final topic, here is the more recent work where instead of taking a typical photolithography based microfabrication approach, what about we utilize the modern techniques to fabricate 3D devices for a variety of applications. So in that case, we have direct laser writing. I utilize this technique to fabricate this prototype. I use a simple PCB base and use the metal on top of that to create a transducer to facilitate electrostatic actuation and capacitive sense. So it's basically a parallel plate capacitor, and here you see on the right top, these are the capacitive gaps which were created by ablating the material on top of the PCB using the direct laser writing micromachining. So this was a very promising research. It can be applied to a variety of materials such as semiconductor, conducting ceramics. We don't need any foundry tape out process or typical clean room. We just go for the research or industry collaboration and submit our requirement there. So here is the finished part. This paper was also published with the microsystem technology with the Springer Nature, and this is the first time demonstration of using this laser micromachining to demonstrate a fabricated transducer. So here are the elementary results, that is the resonance as a function of applied perturbation. Here again different outputs such as resonant frequencies in the bottom, and here the amplitude shifts. This graph shows how these two different output varies as a function of applied perturbation. So again, the amplitude shifts apparently were much higher, and therefore this was proposed to be sensor output. I would like to conclude this research seminar by acknowledging all these organizations in past few years who gave me this opportunity to pursue and demonstrate my research, including my PhD research institution, my collaborators, and as a researcher the institutes in India as well as at the international platform where I have worked. Just last slide, as I was asked to present my research vision. So currently I'm quite active in biomedical area side, VLSI designing, with the focus on MEMS and IC integration and tape out processes. I would like to utilize my prior experiences and expertise to establish a broader research and innovation activities in this miniaturized structure, sensors and systems, and especially with the focus of their integration, whether on the PCB or in the silicon die, towards electronic integration to develop modern products and research. Goal is to disseminate the research results in the top international avenues such as conferences, international top conferences and the journal. I would like to extend my skills and provide training and supervision of research projects with the students and the fellow researchers, and therefore I look forward to sustain my global scientific outreach. So these are the areas, sensors and actuators, MEMS and IC design. I'm little bit exploring also, but that is just to give students and equip them with the required skills. So I'm also exploring this area of embedded electronics. Again, biomedical also I'm pursuing. So with that, I would like to stop here for this research presentation. Thank you very much. In case you have question, please let me know.